Hello, everybody. I hope everybody can hear me and see me. Today, apparently, I had no problems with YouTube. For the first time, I don't get an error in like 2 weeks. Today, we're going to talk about Mr. Al-Khalili and his version of electricity. What do we know about electricity? Well, we'll let Mr. Al-Khalili tell us what he knows about electricity. Okay. Well, he starts with a little bit of history of electricity. He starts with this fellow. Covered him in the past. His name was Francis Hauksbee. He was Newton's right-hand man, and he was the guy who did the experiments for Newton, essentially, after Robert Hooke died. So that's when Newton took over the Royal Society and brought this man in to do his experiments. This fellow was more or less like the Faraday of his day. He was the guy who was in the lab doing the work. And he came up with this little invention, Hauksbee machine, that produced a bluish glow when he rubbed it. It was static electricity. The issue here is that he was British, and that's, I guess, why Al-Khalili brings him up. He could have started a little earlier with this fellow. I think was probably a little more important, and that was Otto von Guericke in Germany, and he did the same trick, but he did it with a different material, ball made out of a different material. It's Hauksbee who comes in there and does it with glass. Okay, but anyways, that's a brief introduction that Al-Khalili does. Then he moves into what was quite famous in the 18th century, which was this Leyden jar. Okay, I covered that in the past. And essentially, all these people were charging the glass ball, which Hauksbee had come up with, and they were doing all kinds of tricks trying to figure out what electricity was. And that moved along throughout the 18th century. You have all the way to Ben Franklin, which a lot of people have heard of, especially in the States, flying a kite and doing his little experiment with a key. Supposedly, some people say he never did the experiments, others say he did. It's not very clear. But things really get rolling in the 18th century when we have a fight between these two fellows. Mr. Galvani and Alessandro Volta. And you could say that it was a spaghetti war. Galvani had discovered that frogs, when he put a little electricity through their legs, they moved their leg. And first, Volta, who was a physicist, supposedly a physicist, he liked the idea, but then he later on said, no, look, the reason he moves the legs is he's just a conductor. It's the plates that you have at the ends that are producing the electricity. And so, yeah, they went back and forth, and Volta eventually invented what is known as the pile. And you can see why it's called a pile. It was a pile of metal there with divisions there. And essentially, that was the first battery. Okay, so Volta comes up with a battery. He's been honored by using his name for the name volt, for the value known as volt in mathematics. And yeah, all these people were playing around with electricity, or what they did not know about electricity was static electricity, until things got a little more involved, and you get all the way to Davy, who is the person who is going to produce the first arc. In other words, he's going to take two poles, and he's got it tied to gazillions of batteries, and he produces an arc right there in space. So an arc light. In other words, it was a very shiny light. And they said, well, it's great, it's a great magic trick, but what can we use it for? We can't light a house with that, it would make everybody blind. So that didn't go very far, but it was a nice little trick. And they were doing essentially tricks throughout the 18th century, what were known as, Al-Khalili says, they were known as electricians. And electricians were essentially magicians. They would go there and do all kinds of tricks with your hair, you know, rub your hair and pull it up, or pull some feathers or whatever. And they were just tricks. And of course, none of them had any idea how all that happened. Okay, so that's the important, that's the scientific part. Okay, okay. Al-Khalili then goes in there and says the following. He says, mid-18th century electrical philosophers, or electricians, right, were faced with this challenge. What electricity was, how it worked, and why it did all these things was nothing less than a complete mystery. So again, they had no clue whatsoever. The biggest surprise for Volta, right, was that the electricity it generated was continuous. Okay, it poured out like water in a stream. Now listen to this. And just like a stream where the measure of the amount of water flowing is called a current, so the electricity flowing out of the pile, you know, that little pile that he made, became known as an electrical current. So this is where we get the notion that we have something flowing. And this is going to be so bad for humanity, because now we've had 200 years of this flowing stuff. Nobody knows what's flowing. They say it's electrons, but then they can't explain their atom. So what is it that's flowing? You know, is it electron beads? Individual discrete electron beads? Is that what's flowing there? Tons of them? And yeah, that's what we have today. But this is where it starts. It starts with the notion that people use the analogy of the current, of stream current, of river currents to simulate or to think about electricity. They were thinking in those terms. Okay. So Al-Khalili continues. He says, 200 years after Volta, we finally understand what electricity is. Do we? I mean, do they, the mathematicians? We do, but the mathematicians know what electricity is. The atoms in metals, like all atoms, have electrically charged electrons surrounding the nucleus. Oh, is that so? Maybe they can draw an atom for me. Does it look like that thing there on the top upper right? Is it an electron bead rolling around a proton ball, bowling ball? Is that what it is? Is that what an atom looks like? And the only question there again is, how is the electron bead, that little thing that's going around, how is it tied to the nucleus? Why doesn't it spontaneously run off, you know, and do ionization? Why does it stay physically bound to the nucleus? That's the only question any theorist has to answer that proposes this model. And if they can't answer that question, they can't even start, because what they're going to argue is that electricity is going to be the flow of all these electron beads. And the question again is, what compels them to move? Are they hit with stones? Is that how the first one starts moving? Is that how the trickle starts? Do they get hit by something? So we've got two problems. The first one is that we cannot explain how the electron bead remains faithful to the nucleus to begin with, and then what compels it to leave the nucleus? What is this force, this spirit that enables the electron to start its journey? Okay, keep those two things in mind. Okay, but in metals, the atoms share their outer electrons. Share? So I've got a little electron, the other guy's got a little electron. What do you mean we share? We exchange them, we put them on the same level. In what way do we share them? How do you share an electron? And again, what holds that electron bound to the nucleus to begin with? Okay, but all these issues come up because they're structural issues. What does an atom look like? That's going to be the issue. But he says it like, you know, it's a done deal, you know. And he said, but in metals, the atoms share their outer electrons with each other in a unique way, which means they can move from one atom to the next. So if they share, what's that got to do with moving from one atom to the next? Again, there's a lot of stuff that he's bypassing. He's just rolling over here. Like, We know it all, right? But he hasn't explained anything. He's got to explain why the electron doesn't leave to begin with. Then why does it share? What do you mean share? And then if they're sharing, like they're occupying some level out there, what compels them to start drifting and moving from atom to atom? All these questions are never answered. They talk about concepts, abstract sounds, fields, forces. What are those? Charges. Those are not physical objects. And yeah, there you have the little picture of how they visualize these electron beads moving around the metals. And the question is, what compels all of them to start drifting in a single direction? Okay, so what is electricity? Well, he says, here it is. He puts on his caricature hat now, and he says, if those electrons move in the same direction at the same time, the cumulative effect is a movement of electric charge. Charge moves? What is a charge? I thought charge was 1.6 times 10 to the minus 19 coulombs. And that's a value, that's a number, that's amount. That's not a thing. That's not a thing I can hold. So how can I have a movement of charge? Are they talking about, is it electrons that are moving? Or is it that they're measuring this charge flowing with some meter, and they're saying, oh, the flow of charges. So they're cutting a lot of corners here, because they go from objects all the way to concepts, to mathematical concepts. They start by saying, look, this is the electron. What is an electron? It's a charge. What's a charge? Oh, we don't know, but it's what we measure it. And it's measured at 1.6 times 10 to the minus 19 coulombs. And when we have lots of those, well, we have a flow of charges. We call that electricity, or current, or whatever. This flow of electrons is what we call an electric current. Okay, so now you know what an electric current is. It's a flow of charges. It's all these concepts, these mathematical concepts that are flowing. Well, the 19th century, you had people like Faraday and Maxwell. They became famous in that century. Why? Because they were able to play around, Faraday with experiments, and Maxwell with mathematics. But it was a world in which people didn't really care about electricity. What was electricity? Nobody cared. People wanted to make money, just like today. Most people don't care about what is electricity. What does an atom look like? People don't care about these things. The majority of people out there, 90% of humanity, doesn't care about these things. They care about making money. They care about everyday stuff like going to work, making money, see if they can get rich, win the lottery. They have other things on their mind, girls. But they never think in terms of, oh, what is electricity? How does it flow? What does an atom look like? They never ask these questions, or they very seldom just, touch these subjects. And so they make a comment here. Al-Khalili makes a comment. He says, look, while Faraday continued his work trying to understand the very nature of electricity, inventors from across Europe were less interested in the science and more interested in how electricity could make them money. The more things change, the more they stay the same. And we haven't changed a bit in 100, 200, 300, 400 years. People are not interested in these subjects, so they want to make money. They want to say, what's it good for? Tell me what I can use it for. What can I invent? What can I sell? So they don't ask the fundamental questions like, what is and why does it do this? Why does it behave this way? In other words, cause, mechanisms, right? What's certainly quite remarkable from a contemporary perspective is that by and large, nobody seems to really care very much what electricity is, right? You're talking about today, right? You don't have great theoretical debates as to whether it's a force or a fluid or a principle or a power. What they're really interested in is what electricity can do. Don't ask what you can do for electricity. Ask what electricity can do for your pockets. That's what science has become. In other words, people are not interested in the subject matter, and therefore you can tell them whatever you want. You can tell them that electricity is the flow of angels. And as long as you have, a PhD in math, you can convince us, hey, that's what we've proven. We've proven it with experiments. Here's the equation. What's the guy going to do? Challenge you? He says, oh, well, you know more than me. So you can sell people who are not interested, who are very apathetic to these things. You can sell them anything, and that's where we are today. They're selling them a lot of stuff like electron flows and charge flows and so on. Okay, but that brings two fellows who were making money or trying to make money. And it's these two gentlemen. They worked with electricity, not so much with electricity. They weren't interested in, again, in the science. They were just doing things every day to try to figure out how they could make money. They were businessmen. They were not inventors, and they were not scientists. Okay, so we have, especially Edison. We have him as a god. You say, oh, Edison, the Wizard of Menlo Park. That's where he had his company, and he wasn't even an inventor. He was just a businessman, a good businessman, no doubt about that. You want to have him as an icon for business, that's fine. But what is an inventor? An inventor is a guy who sits down and thinks and tries to figure out, a new machine or a new device or a new way of doing something or making something. And Edison, he started out like that. Later on, he abandoned that. He was more into business. He was trying to make contracts and so on. And he made a contract with this fellow, with Joseph Swan, in fact. They created a little company. And why? Because Swan had a few patents, and Edison wanted access to those patents. He had some other patents. And so, it was the hunger and the eagerness to eat that got together with these two fellows. And what they did was they formed a company and they put their patents together. Okay, and that's what they did. They started to make money. And you look at when Thomas Edison was born. He was born in 1847. He was only 3 years old when Swan began working on the light bulb. So, Swan had quite a bit of head start over Edison in many ways. So they say, Edison's the inventor of the light bulb. In that sense, Al-Khalili is right. Edison is just a moneymaker. That's all he was. He was not a scientist for sure. He never knew anything about electricity. He just tried different things, especially to come up with his filament. And he tried one material after another. Does that make him even a hero? No, it's just the fact that he was at the right place at the right time. He had the right tools. That you can give him credit for. The fact that he was lucky. He was where he was supposed to be. He built this empire. Fine. But that's got little to do with him being an inventor himself. Okay. In fact, he had on board this other fellow who was Tesla, who worked a while with him, then went to work for the competition. Okay, so what did these guys do? All these people worked on making money. This is what they did. They all worried about making money. That's what their goal was. That's what they had in their mind. Okay. So both these fellows, they formed this company which was known as Ediswan by a lot of people. I don't think that was the official name. In what were considered to be independent lines of inquiry, Swan's incandescent electric lamp was developed at the same time as Thomas Edison was working on his incandescent lamp, with Swan's first successful lamp and Edison's lamp both patented in 1879. That's how old these lamps were, okay? And they were attempting to replace the heating lamps, right? Edison's goal in developing his lamp was for it to be used as one part of a much larger system, a long-life, high-resistance lamp that could be connected in parallel to work economically with a large-scale electric lighting utility he was creating. He was trying to sell a utility, not so much lamps. He was trying to sell both, really. Swan's strong patents in Great Britain led in 1883. Swan's original lamp design with its low resistance, the lamp could only be used in series, and short lifespan was not suited for such an application. So Swan's strong patents in Great Britain led in 1883 to the two competing companies merging to exploit both Swan's and Edison's inventions, with the establishment of the Edison-Swan United Electric Light Company, known commonly as Ediswan. The company sold lamps made with cellulose filament that Swan had invented in 1881, while Edison company continued using bamboo filaments outside of Britain. In 1892, General Electric, which was what this company became, right, began exploiting Swan's patents to produce cellulose filaments until they were replaced in 1904. Okay, so these guys were businessmen. In fact, if they would have known a little bit about electricity instead about doing business, signing contracts and that sort of thing, lobbying, what they would have done is they go out there and study materials like semiconductors, etc., and they would have probably made a lot more progress. They were interested in making money. So in science, they're not heroes, okay? But then were other people heroes like Tesla, which is, here Tesla is a guy who's glorified by the electric universe and by the flat earthers and all these locos out there. All these people care about the good old Tesla. And what happened, Tesla was used to work for Edison. Then he went to work for the competition for George Westinghouse, whereas Edison was banked by J.P. Morgan. So here were two rich guys behind these two corporations, really, or entrepreneurs. And one of the big wars that Al-Khalili talks about is the fact that, it's known as the current war or the war of the currents. Edison liked direct current because that's what he was up to. And Tesla had come up with alternating current. And eventually Tesla won. He won a big contract to get power out of the Niagara Falls. And because of that, Westinghouse did pretty good. They were able to impose alternating current. By that time, Alva Edison had also branched off into other devices, the phonograph and so on, so he had several products. His company had grown by then. So it was a bit of a loss, but not a fatal loss under no circumstance. In fact, it was the other way around. The guy who's going to be left out would be Tesla, okay? Yeah, and Tesla was not a scientist. Neither was, just like Alva Edison wasn't a scientist. Tesla just tried one thing after another. Did he have an explanation for what he was doing, for what electricity was, how it operated? No, he was using the same atom as everybody else. And if anything, he worked with waves, that he didn't understand. He talked about fields and energy. So obviously he had no clue whatsoever about science. And that's what the words that were used in those days, and they're even used today. So nothing has changed. So Tesla could not have been a scientist, okay? Was he an inventor? Well, if you call an inventor a guy who imagines and invents something, comes up with a new idea, yeah, in that sense, he could be an inventor. Another thing is what Alva Edison did, which was just try one thing after another mechanically until you figure it out. Anybody can do a lot of this by trial and error. You take a magnet, you pick up pins, and then you say, well, what if I want a stronger magnet? So you try a stronger magnet, and you say, oh, this one has a different behavior. And then you use that for some purpose. That's what all these people did. Is that an inventor, or is that just a guy who goes in there, is in the lab, and just tries one thing after another, and ideas come to his mind? Nice to be in an island and not have anything at your disposal and just visualize and then come up with things. Now that would be an inventor, in my opinion. But a guy who goes to the lab because he's got a job, because that is his job, his livelihood, and he goes in there, tries different things and discovers things while he's doing things like Faraday did, I don't call those inventors, really. Yeah, they came up with inventions because it's what research and development sectors do today. They go out there, they have all these people, they work in different things, and they come up with a new idea. Who's the inventor? The team. Why? Because this guy pitches in something, the other guy pitches something else. And that's more or less how these people worked as well. They saw something, they were bright people, no, not taking that away from them, but that's not the same thing as just being isolated and visualizing, okay? Now, Tesla did a little bit of that. He did visualize things and then try to put them into practice, okay? In that sense, he was an inventor. But if he just went into the lab and tried different things and then came up with something like Alva Edison did, well, then he's not an inventor. So, as far as I'm concerned, the jury's still out with Tesla. I don't know if he was an inventor or not. Certainly, he was not a scientist. Scientist is a guy who can explain, not a guy who can come up with a device or can say, oh, wondrous lies like this charlatan did all the time, promising so many inventions to the world and supposedly died with them. And everybody saying, oh, the FBI went in and took all his secrets. Poor old Tesla. Yeah, I think he died penniless. He was found in a hotel room after 3 days of being dead. Okay, let's move on here. Organize myself here a little bit. Got so many of these little things. Okay, so here Al-Khalili continues, and he says, in the 1880s, people were terrified by electricity. Yeah, they had heard that people could get shocked and so on. It could shock and even kill in an instant, and the reasons why weren't fully understood. So people had no idea yet what electricity was. They were able to develop devices. They had the telegraph by then. Okay, they had all these nice little toys. The telephone was in those days also in the process of being spread around. And we had these little toys out there, but nobody knew how they worked. In other words, no one understood electricity. Okay? And this is the key, because that's the science part. The rest is all technology. And I guess you know where I'm going with all this. Yeah, technology and science never shall meet. They're two different things, completely different. Okay. So how does Al-Khalili continue? Well, he says, after centuries of man's experiments with electricity, a new age of real understanding was now dawning. Was it? Understanding, like, not description, but explanation. We're not talking about being able to describe and put an equation, describe it mathematically. We're talking about, can you explain? Okay. Surrounding any electric charge is a force field. What the hell is a force field? Is it? I think I've got one here. Give me a second. I can get it up here. Is that the force field? We've got it today. The force, may the force go with you, Michael Faraday had proposed a theory that says that a flow of electricity could in some way create an invisible force field, whatever that was, okay? I guess it's what comes out of the swords there. Is that what a force field is? That's what happens when you invent concepts and you do not really know what you're talking about. So you invent these abstract concepts, mathematical concepts primarily, but it could be qualitative ones as well. And they're concepts, and people treat them like objects. So they say an invisible force field. Hopefully all fields are invisible because they're concepts. We can't see any concept as far as I'm concerned. James Maxwell proved Faraday correct. Correct? Proved? You see how they use these words. It's like a done deal. You have to accept it. You got to memorize it because it's already been proven and it's correct. It's true. And so what did they prove? That there's a force field, that there's a concept, that there's an invisible concept? Yeah. I guess he proved that much, okay? Not through experimentation, but through mathematics. Maxwell's calculations showed how these fields could be disturbed. How can you disturb a concept? How do you disturb love? How do you disturb information? What do? You shake it around? So again, these people are using objects as concepts, and that's what pervaded the language. We've had this language at least for 100 years, if not more, and that's been the bane of science. Okay, changing the direction of electric current, you could create a ripple or wave. A wave? What's a wave? Through these electric and magnetic fields. So now we have a wave in fields. I mean, it's like saying, are we talking about wheat fields, corn fields? If there's a wave, like the wind comes over, moves the cornfield, the corns, each one of the stalks, and we see it from afar, say, okay, there's a wavy motion But what's the object? The object are the corn, the stalks. Those are the object. What's the object here? It's the waving of fields. What's a field? When a field is a bunch of numbers around an object. It's a value at each point in space. That's what a field is. Now they're moving all these concepts. They're waving the concepts. And it says waves that would carry energy. How do you carry energy? Like on your back? You can see none of this is an explanation. It's all gobbledygook language. They're moving love around. They're moving grace, hatred. That's what they're moving around. And they're saying, oh, we have the vibration of energy or the carrying of energy. How do you carry energy? Until something absorbed them, you're going to absorb energy, okay? Waves could spread through these fields like ripples on a pond. Yeah, I guess the magic show just started. They started moving all these things. Okay, and one of the fellows who made it kind of visible was this fellow, Hertz, And Hertz designed experiments to prove that Maxwell waves really existed. Here we have Maxwell proving Faraday. Now we have Hertz proving Maxwell, okay? Hertz built a device that could actually create and detect these waves as they pass through the air. You could detect them, create and detect waves. What are you detecting? What you have to detect is the object, not the wave. It's like saying I detected the ocean wave. Yeah, but what's causing the wave is the water. So you have to refer to the water always. You can't just continue talking about the wave as if the wave were an object. Wave is a verb. Wave is what the ocean water does. Ocean water is the physical object, the one made out of atoms, etc. Wave is what it does. Wave is a verb. Wave is an action, a phenomenon. You can't use it as a noun as he's using it in every single sentence here. He had detected Maxwell's waves traveling through space. And more nonsense. Through space, space is nothing. How do you travel through nothing? You can travel through something. You can travel through molasses, water, air, or if you're Superman or whatever, the Flash, you can maybe travel through iron. I don't know. But these guys are traveling through space, through concepts, through nothing. And they have these waves traveling through nothing. So we have wave, which is a concept, it's traveling through nothing. You figured it out. After centuries of man's experiments with electricity, a new age of understanding was really dawning. Yet Oliver Lodge exclaimed, okay, we have enslaved that all-pervading ether. So here, they said we have a new dawning of understanding, and this guy is talking about the ether. And so a couple of years later, or around the same time, 1881, I think it was, to 1887, Michelson and Morley showed to the world, at least to the mathematical community, that there is no such thing as the ether. And so this guy, I don't know, he's talking about the ether. You figure it out. So was it an understanding, or was it that they thought they understood? This is the question you should ask. Did these guys really understand? And here's the ether, okay? Bunch of particles. And what are they saying? Is that a wave? The waving of the ether? Are the particles shaking up and down? Is that what's happening? Is that what a wave is? Okay, so yeah, it's all these deranged people from the electric universe and flat earthers and quantum mechanics. They talk about waves and particles because they never have to explain what moves the particle up and what moves it down. Why does it wave? Why does it oscillate? That's what you got to explain. You got to explain the cause, the mechanism. And to say it does so, well, yeah, if it's a particle. If it's not a particle, maybe it does not so. Okay, and so he went a step further and he said, could the electric current pass through nothingness, through the vacuum? Good question. How can you pass through nothing? You can pass through something, but it's very hard to pass through nothing. You can't cut across nothing. You're not occupying locations in nothingness. You can only occupy locations with respect to other objects, atoms, for example. Okay? then you can say this atom has a location with respect to all the other atoms in the universe. Then you can talk about location because you're talking, the reference is all the rest of the atoms in the universe. So you have a distance with respect to each one of those. Then you can talk about location. This guy's talking about going through nothing. Like if it's a little ball, the only ball in the universe, right? It's the only object, and it's going traversing, it's cutting across nothing. With a Crookes tube, could finally see electricity. The CRT was born. Yeah, the Crookes tube was essentially what was going to become the CRT, the cathode ray tube. Okay, and did we understand it? Well, they gave it an explanation, which lasts to this day. Okay, and the question is whether that explanation is correct, whether the mechanism that these people are talking about is correct. And here it is: the electrons only moved in one direction. Electrons, how did they come out of the atom? How were they stuck to the atom to begin with? Why didn't they spontaneously come out? Why did they need something to push them? If that's what happened, I mean, what compelled them to move? From the heated and metal plate through the positively charged metal plate at the other end, we discovered how to manipulate electrons flowing through the vacuum. That's the quantum mechanical version. That's where he gets this. You have just electrons flowing through the vacuum, okay? Let me put a comparison there so you can see what the difference is and where the problem is with this. Here's classical electricity, okay? Here you have atoms, and what the electrons do is they move from atom to atom. That's different than what quantum and Al-Khalili say, which is just electrons moving through the vacuum, no atoms there, okay? And of course we have our rope model, okay? And that's, just a twirling of electron shells, which are all merged in a single row, okay? Now what happens? If you pump the vacuum chamber down and you go beyond -7 torr, you're not going to get electricity. You're not even going to get an arcing after a while, okay? So if you keep pumping down like to the moon level, to the -12 torr level, you will not get an arc. That already destroys the religion of the electric universe. The electric universe is talking about plasma electricity out there in space because they have to explain gravity, right? That's how they explain it. And where's the plasma? I mean, they know or they accept, as far as I know, all electric universers, they concede, okay, that man went to the moon. Some people don't, but as far as I'm concerned, officially, the electric universe says, yeah, man went to the moon. They even have shots of Mercury and the moon, which they take from NASA and they put on their website. That means they agree that humans have gone out into outer space, unlike the flat earthers who say, these guys never went there. Okay, so there's a difference there. Okay, so man went through the moon. Apollo 14, Apollo 15, they put a cold cathode up there. And they measured the vacuum on the surface of the moon. There was one probe also that measured the vacuum in empty space as it was traveling somewhere between the Earth and the moon. Also, both those readings came out in the -11 and -12 torr range. You cannot produce electricity with such low vacuum. Electric universe people need to understand the ABCs, okay? So it's just totally nonsense what the electric universe proposes, that gravity is electricity. Okay, it's absolute nonsense. No chance whatsoever in science, by the way. Okay, so what does Al-Khalili conclude? Because, I mean, you would think that he's something better than the electric universe. No, he ain't. He's partly because the electric universe takes its cues from quantum mechanics. Okay, they use the same atom. That's the problem. And so again, there's your atom. Please explain why that electron bead doesn't fly away. What keeps it bound to the proton? Why does it jump? What causes it to jump inwards and jump outwards? And they say loss of energy. Energy is a concept. What did it lose? Did it lose 3 pounds of iron or something, and that's why it's lighter, now it fell inwards? What did it lose? What did it gain when it gains energy and jumps to a higher energy level? What the hell are they talking about? What are these energy levels? Are they balls? Are they spheres, membranes that encapsulate the proton? Or are they just regions, concepts, where we can find the electron bead? Those are the issues that need to be resolved before anyone has a theory. Okay? You can't talk about a theory about electricity or about ionization until you tell me what your atom looks like. And if that's your atom, you got a lot more questions, because how does that electron stay bound to the proton, to the nucleus? And if you can't answer that question, you can't even start your presentation. The microphone is withdrawn. Al-Khalili said it was in the early 20th century that we finally discovered what atoms were made up of and how they behave. Did we? Did they? He's talking about Rutherford, essentially, right? And so what electricity actually was at the atomic scale. I don't think they know what electricity is at any scale. They use it. They can work with it like we can work with magnets. That doesn't mean that he understands what a magnetic field is. And likewise, he doesn't understand what electricity is. He thinks it's a flow of electric beads. And then all he's got to answer is that atom. We take them back to the atom. Anyone who uses that atom to do its electricity or your ionization or whatever, magnetism, we take you back to the atom. What does your atom look like? Please draw your atom. If you tell me you don't know, you can't start. Because we don't care about Mother Nature's real, genuine, super duper, honest to goodness atom. We care about your atom in order to understand your theory. So you have to draw your atom and defend it. You have to defend it against Bill Gates' attacks. Okay, I'm going to attack that atom. I'm going to let you do your presentation with that atom. So if you do electric universe stuff with that atom, you do flat earth with that, you do quantum mechanics with that, I'm going to attack your stupid atom. That atom doesn't work. Okay, you can't justify it. And you can't justify it with concepts saying, well, you have this field and we have the charge. Now, tell me what physical object is between the proton and the electron. That's all you got to do. You got to draw something in there. Okay? And yet the explanation today is, advances in radar technology during World War II led us to tinker with semiconductors and gradually phased out valves. Okay, we started with valves, which was a modification of the CRT of Crookes tube, and then we moved on to semiconductors. And yet the explanation today is that photons are knocking electrons out of the atoms, despite that no one can illustrate an atom or explain how the electron bead physically remains bound to the nucleus. That's my statement there, before it is excited out of the nucleus, or out of its orbit. So that's what a person has to answer. What keeps it bound to the proton, what excites it and takes it out of the atom so that the atom is ionized and now you have a flow of electrons. And if you have a flow of electrons, what keeps them moving, what keeps them flowing in one direction? Are they being pushed? Are being sucked from the front, like a vacuum cleaner? You got to explain the mechanism. You can't just say, well, they flow. That's a description. I need a mechanism. And of course, for a mechanism, you're going to have to start at the atom. So good luck with that one. I like Bohr and Heisenberg, which I mentioned the other day. They said you cannot even imagine, so don't even try to imagine or visualize the atom, the quantum atom. So anyone who tries, like Bohr said, is an idiot. He called Feynman an idiot because he tried to convince the crowd that, you can visualize this. Look, listen to me a second. No, Bohr said, I'm not going to listen to you, idiot. So, you cannot visualize the quantum atom. It's the bead, the particle atom that you cannot visualize, because you cannot explain anything with that atom. So if that's your atom, and that's the one you learned by rote in high school or college, you're going to be in trouble in this site. Okay, in this site, you're going to be in definite trouble. So you better forget that atom. Okay, we have a different atom, as you all know. Okay. Anyways, here's my summary, my conclusions of good old Al-Khalili. He does a good job in reciting, historian, right? No problem there. The history of experiments that led to the discovery and description of the electricity. Description! That's all they did. They described, and they described the invisible stuff completely in an irrational way. They described it with little balls, and their math described also the little balls. So it was always a little ball world. And little balls can only push. You can't pull with balls, with discrete balls. And that's what separates it from the rope model. The rope model, for the first time in history, introduces pull, the force of pull. There's never been a force of pull. They always did it in a Ptolemaic way. You know, they did it through push. Push gravity, like a couple people out there. What was Van Flandern was one of them, Tom Van Flandern. Push gravity. To this day, the mathematicians and experimentals have no clue what electricity is. They don't. They have no idea. They use it, and they consider that now classical mechanics, so nobody deals with that. Everybody's into quantum and string theory and relativity. Nobody deals with this stuff anymore. So they learn whatever they learn in high school, and then they forget about it all completely. You say, oh, that's classical mechanics. It's got no future. So nobody knows what electricity is because everybody just learns by rote whatever they learned up to high school, and then they just repeat it from then on. Nobody ever decided to question whether the particle model of the atom and of electricity have any validity or are even possible. And here people like Bohr and Heisenberg, who studied in great detail all this stuff, they tell you, look, you cannot picture the atom. We cannot explain it with this atom. So quantum mechanics is based on an object called the atom, which no one can illustrate for you because whenever they do it, they can't use that atom to explain anything. And if they say, well, we can explain ionization, we can explain electricity, you take them back to the atom, you say, what keeps the bead bound to the nucleus to begin with? What compels it to move? And we're back to square one. Quantum cannot explain those except through descriptive words. In other words, they use the words of mathematics: field, wave, particle, zero-dimensional point particles, right? So they use all these nebulous terms to get their theory across. But when you put them to the test, what's a field? Well, it's a bunch of numbers. What's a charge? Well, it's a number. It's 1.6 times 10 to the minus 19 coulombs. And all you get is all these abstract mathematical concepts. That's what they're moving. That's where the problem is. We don't have a mechanism. Al-Khalili actually proves that experiments in math cannot tell you what an atom looks like or how Mother Nature does electricity. That's my conclusion. Questions should be addressed in that direction, okay? Okay, we have questions today. I'm going to get the fan mail, but today what I'm going to do, let me put this over here. I'm going to answer a single guy today, okay, because he raised several questions. I thought they were all very pertinent, very important questions. They're questions other people like answered. So since he put so many questions, so many issues that he raised, I'm just going to answer him today. I'm going to leave some of the other questions till Wednesday, okay? So let's get started with this gentleman. And he doesn't agree with me, but that's irrelevant, okay? Important are the questions that he raises. Okay, here's the first comment or question. And he says, this fraud called the Heisenberg uncertainty principle, mathematician, BS. Yeah, I kind of agree with him. This is my answer. In Heisenberg's own word, the more precisely the position is determined, the less precisely the momentum is known in this instant, and vice versa. Okay, that's out of his paper, the one he got the Nobel Prize for, essentially. Heisenberg indeterminacy simply states that the more a ball stands still, the less it moves. And the more it moves, the less it stands still. That's in a nutshell what Heisenberg says. And there you have it. Change in position, as they called it. What is position? Well, in mathematics, position is motion. They just called it position, but what they're talking about is distance traveled from a given point. So position for them has a numerical value, which they're going to put in an equation. So even though position is a static concept, they use that word to refer to motion. So there is no difference between position and motion in the religion of mathematics. And then motion, which is that delta P, which is momentum, and I'll just call it motion because that's essentially what momentum has to do with. So we have location times motion, and when you increase one, you decrease the other. And both of those have to be greater than that constant that's on the right. That's essentially what Heisenberg's equation states. That's what he got his Nobel Prize for, okay? And essentially, this is how they model it. Let me get it up here. Okay, when they want to talk about location, position, they're going to use the particle. That's essentially what the trick consists of. And when they want to talk about momentum, they're essentially referring to the wave. So it's like the wave converts to a particle and the particle to a wave. The wave particle duality. That's what's embodied in this. And from that, you have also the principle of complementarity that Bohr came up with. And that says also duality, that light is both a particle and a wave. And this is how they interpret it. They want you to believe that, you have these spherical waves. When a particle hits something, it suddenly, branches out all over the room, okay? And you have to think of these as, having a particle in the center, okay? Because they use it as both. Whenever they want to refer to position, they'll talk about the particle. And whenever they want to talk about the fact that a particle can be at several places at once, what they're really referring to is these waves. The particle suddenly converted into the spherical waves and is everywhere in the universe. So suddenly it goes from pinpoint to the whole room. That's essentially what these people have up there in their minds. And they never discovered Werner Heisenberg or any of these fellows that what you have to discover is that the invisible entity, what entity is doing that invisible phenomena? That's what you got to discover. That's what you got to visualize. And you say, well, why does there have to be an entity? Because if there is no entity, you're doing black magic. You're putting spirits in that same, you're doing something, but you're doing it with nothing, a concept. So you're putting spirits in that same space. You're doing black magic. That's why there's got to be something. You can't do physics without an object. First rule of physics, you got to have an object. Okay? What is an object? That which I shape, not that which you can see or touch. Okay? So you go one day to the forest, okay, and you see a tree, and it looks like this, okay. It's got these markings, these lines around it, and you try to figure out, well, what could have happened, and you come up with a theory. And say, oh, I know what happened. Here it is. I'll illustrate it for you. What happened was a squirrel, kept coming up and down the tree for a long time, carrying his nuts and whatever. And over time, he made that path. He made that itinerary. He carved a groove into the tree. So that's your theory. Okay, that's probably true. I can come up with a different theory. What if it was a snake that slithered down the tree, and over time or whatever, and caused those markings to occur? So I have a different theory, and I come up with a totally different theory based on a different assumption. I'm not saying it's a discrete little rodent that's coming down. I'm saying it's an elongated snake. And another guy may come up and he might say, well, I disagree with both of you. I think it's the vine that was there for a long time and it created that groove. So it's important to determine what invisible entity, you got to try to visualize it, could have caused that. Okay, and you might say, well, let's run a test. Let's run an experiment. And so you do the experiment. You do it 1,000,000 times. It's got to be repeatable to be scientific, right? That's what these mathematicians say. So it's got to be a repeatable experiment. You do it 1,000,000 times. Great. And now you go back to the conference. You say, okay, Joe, what do you think now? Huh? And the guy said, well, I still believe it's not a rodent. I still think it's a snake. The other guy said, yeah, I still believe it's a vine. So no matter how many experiments you do, experiments are only used for proof, for evidence, to convince people, to persuade them to believe like you do. That's the only purpose of experiments, and to maybe to develop technology. trial and error, Other than that, experiments have nothing to do with science. The fact that you do an experiment doesn't mean you understand what caused the experiment, the phenomenon. So the only purpose of an experiment when you take it to a conference is to persuade people to believe like you do. And a lot of people, for as much proof as you present on behalf of God, a lot of people say, hey, I still don't believe in God. What are you going to do? Right? Some people believe in God, some people don't believe in God. And they all have proof, they all have evidence, they all can run experiments to prove exactly their point. The guy who believes in God, he says, look at the bee going around the flower, and who could have created that if not a great intelligence? And everybody's got proof and evidence and experiments and observations. So that doesn't qualify as science. In science, we have to have a mechanism. That's what we're interested in. Okay? And that's what differs science from what a lot of these people do. Okay, here's another comment from this fellow. Got so many of these down here that it's going to take a little while to get them up there. Density is a ratio between volume and weight. We are measuring two qualities, porosity and the inverse mass. Okay, from there we can calculate approximate atoms per volume stuff. Okay, so which ball is more attractive in the Cavendish experiment? Obviously, it's the one higher in mass or less porous. Okay, now go look up definitions of mass, weight, and porous in the dictionary. You're going to see the definitions are correct. There is no reason to be changing these definitions. Okay. Let's see. Let's go to the dictionary. Let's find out what the dictionary says. Maybe I missed something, And yeah, here's what we find. We find the Wikipedia starts out from the go. Says mass is both a property of a physical body and a measure of its resistance to acceleration. Well, hold it. Are we talking about how many particles an object has, or are we talking about how much resistance it puts to you being pushing it? In physical science, one may distinguish conceptually between at least 7 different aspects of mass, or 7 physical notions that involve the concept of mass. So which definition should I use, buddy boy? I mean, they're talking about 7. Let's find out what these 7 are. Let's see if we can use any of them. But certainly I can't look up the definition of mass because they tell me there's 7 of them. So I can't tell you whether you're right or wrong at this point. Okay, here are the 7 definitions. Inertial mass is a measure of an object's resistance to acceleration. Active gravitational mass is a measure of the strength of an object's gravitational flux. Passive gravitational mass is a measure of the strength of an object's interaction with a gravitational field. Energy also has mass according to the principle of mass-energy equivalence. Curvature of space-time is a relativistic manifestation of the existence of mass, and quantum mass manifests itself as a difference between an object's quantum frequency and its wave number. And just in case, you look up special relativity down at the bottom, and special relativity physicists have used different definitions of the term. In these frameworks, 2 kinds of mass are defined: rest mass and relativistic mass, which increases with velocity. So does the number of particles, the quantity of matter, increase with velocity? Does it get fatter, as good old Einstein proposed? If you travel fast, maybe you should travel slower so that you lose weight. I mean, if that's your goal. If you want to gain weight, maybe you just need to go at the speed of light and you'll just gain weight. Hopefully you can keep it after you stop. Okay, so yeah, they have all these different masses. What the hell is all that? And in case you were wondering, you have other sources, okay, because people, a lot of say, but that's the wiki. No, here you get the official sites, okay? Here's University of Northwestern University, mass, how much matter there is in something, okay? And what does Wolfram say? It's the quantity of matter contained in an object. So what do we count? Atoms? And when we do, which atoms is it that we count? So is that what mass is, the quantity of matter, or a measure of the quantity of matter? Here's another site, prominent site, just to make sure that we put some authority here, for those people who believe in authority. And this is hyperphysics, and they say mass and weight. The mass of an object is a numerical measure of its inertia and a fundamental measure of the amount of matter in the object. So which is it? Is it inertia or is it quantity of matter? Measure is when measure is not the same thing as counting. And the one at the bottom, number 2 there, that's counting. The amount of matter is counting number of atoms. And what atom are you going to count? What are you going to use as your unit of mass? And they say if an object has a mass of 1 kilogram on Earth, it would have a mass of 1 kilogram on the moon, even though it would weigh only 1/6 as much. Well, that's strange because the only way we determine mass is by weighing. How do we determine mass? I mean, do you count, when you weigh yourself on a scale, how many newtons do you weigh? No, you look at kilograms and pounds or whatever, but I don't think there are any scales with newtons sold out there, to the public. No, everybody uses the kilogram and the pound for both mass and weight. And no one has ever devised a way to distinguish them. In fact, in the old days, until 2019, the standard of the mass was the Le Grand Kilo in France, right? And Le Grand, if you take this so-called kilogram, right, that lost a little bit in the last century, lost a little weight, went on a diet. If you take it to the equator, it's going to weigh less, different than if you take it to the North Pole. Why? Because the Earth is oblate. That's one issue. The other one is the Earth is spinning around the equator, right, in that region. And the other one, so you're farther away from the center of the Earth. Now, the differences are small, but the point is that you don't weigh. Weight is location specific. That's the answer. So if the Earth moves an inch closer to the sun, it weighs different from the point of view of the sun. Because it's 1 inch closer, and according to Newton's equation, it's going to weigh differently. Okay? It's going to change its weight simply by moving closer. And that means that, weight travels faster than light. Weight is instantaneous because not instant. The word instantaneous is a little tricky. Instantaneous has to do with motion. The correct way of stating it is weight is location specific. You have a different weight at different locations. And if you want to call that instantaneous, then you can say weight is faster than light if you're going to talk about motion. But weight is a static concept. You weigh only a certain amount at a certain location. As soon as you move to another location, instantly your weight changes. It's faster than light. Okay. So if the Andromeda galaxy moves an inch away from the Milky Way, it suddenly weighs differently. That's how fast weight is. The speed of gravity, as they call it. Okay. And because these people have no idea what mass is, they never defined it, we have contradictions. And here's one of the biggest contradictions, okay? And it's the black hole. These people tell you that black holes crush matter out of existence. And one's from the University of Maryland, the other one, University of Toronto, okay? So these people are so-called physicists, physicists, mathematicians, right? And they say that black holes crush matter out of existence, okay? What's the problem with that? Well, because if we define mass as the quantity of atoms of matter, okay, the amount of matter, we have a problem because the black hole is made of mass, right? Because it's a star that's collapsed, right? And mass is the quantity of matter. But matter is crushed out of existence, and we're back to square one. Then what is a black hole? Because a black hole has this infinite mass, but no matter. So we have a circular definition of the black hole because no one defined the word mass properly. What are we talking about? Speed? Are we saying that we're talking about relativistic mass here? Are we saying that the more something moves, the more it weighs? And here we're talking about, quantity of matter because we're only talking about how much a star's mass was compressed, right? So if it compresses and it crushes it out of existence, what's left? we have no structure. And if we have no matter, we have no mass. And if we have no mass, we have no black hole. So we got a circular definition, and that's got to be resolved. And of course, nobody answers that question. Okay. And you might say, well, is that true, Bill, that stars crush matter out of existence, become zero-dimensional? You know, JFG, Guericke, he didn't believe that mathematicians really say that black hole is crushed out of existence, that crushes matter out of existence, that there's nothing there, it goes to zero-dimensional, zero size, zero volume. He says that's not true. Well, he's just ignorant in the matter. That's what it is. Okay, here we have some authority. Okay, let's put some authority so people understand what the issues are. Okay, we have Mr. Hawking. I mean, how much more authority than that do you want? I mean, the only prize he didn't win was a Nobel Prize. He got a Wolf Prize and a couple others. He was knighted, so he's got the authority. He's got all the medals, you know, pinning from his chest, right? And he said, Chandrasekhar calculated blah, 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 blah. Eddington was shocked by the implication, and he refused to believe Chandrasekhar's result. Eddington thought it was simply not possible that a star could collapse to a point. Einstein himself wrote a paper in which he claimed that stars would not shrink to zero size. What is a black hole? What is a singularity? Zero size, zero volume, a point. There's nothing there. There's no structure, no architecture, no matter. So don't tell me that the official, mainstream, that the party line, that the catechism is not that, a singularity is zero dimension. Yes, that's what these people are saying. They're saying structure has disappeared. Architecture has disappeared. There's nothing there. There's zero volume. There's zero radius, zero diameter, zero size, zero D. No dimensions. Okay, you got that? So please don't tell me the opposite, because here you have authority telling you, okay? I had to put these things because people try to get around this. They say, well, that's not what the mathematicians say. And, as the punchline, I always like to introduce Mr. John Wheeler. I mean, how important was John Wheeler, okay? Good old Wheelie, okay? And what did he say? Well, he wrote in his book, together with Edwin Taylor, nature does not offer us any concept as the amount of matter. History has struck down every proposal to define such a term. Even if we could count number of atoms or by any other counting method try to evaluate amount of matter, that number would not equal mass. So whatever you learned in high school, whatever they taught you, especially in high school, but they also repeat that in college, if that's what they taught you, it's wrong. It's irrational. We don't have a definition of the word mass. Whenever you find one, please be nice and post it. That way we can criticize it. We know what you're talking about, right? Okay, another comment also from this fellow. All these comments were the same fellow, okay, and he brought up some important issues, so I think they all need to be addressed, okay? And I think it enlightens other people as well, okay? The universe doesn't exist. He's questioning my statement. Bloody hell! What definition shift game went on here to make a statement like that? The universe doesn't exist because exist hasn't been defined. Okay. So let's do some science instead of emotion, right? Let's go with science. Okay. What is science? Well, we begin by definition so we can communicate our ideas. We don't bring definitions of ordinary speech. We define words that are critical. Obviously, it's critical if we're going to talk about exist, universe, right? So we start with the word object, that which has shape, not that which you can see or touch. What is space? That which doesn't have shape. It's a concept. It's a synonym of nothing, a void of vacuum. Location, the set of distances, okay, between two objects, obviously, or between one object and all the rest, okay. Exist, and again, distance separation, okay. It's physical. We're talking about in the context of physics, right? All these definitions. Exist, object plus location, physical presence. Okay. Matter, objects that exist, and universe, matter plus space. That's what universe is. Universe is a concept because it includes two, a relation, and a relation is matter to space, and space is a concept. means nothing, literally. Concepts can't be said to exist, not in physics, because what does exist? Object plus location, not concepts plus location. Okay, so you need location and no concept has location. So it's straightforward. You just have to apply the definitions. Okay, you don't like the definitions? No problem. Come up with your own. We'll be glad to tear them apart because I'm sure you haven't thought about them. Okay, been at it for at least 20 years with these definitions. Only objects may be said to exist. Okay, so concepts do not exist, and universe is a concept. And so concepts do not exist, meaning that the universe does not exist. Not for the purposes of physics, you cannot say that. In ordinary speech, we say love exists, the universe exists, space exists. In ordinary speech, you can say whatever you want. And that's why it hurts your ear, because you hear this in a physical context, and immediately you're thinking of the ordinary speech context. And you say, hold it, what do you mean the universe doesn't exist? Because you're thinking in ordinary speech. We're talking about strict scientific language which we defined, and we defend each one of those definitions so that we can talk consistently, so that we do not stray on tangents and get lost in ordinary speech and in ordinary language, in ordinary notions that people have that say, well, yeah, the universe exists, yeah, love exists, well, yeah, data and information exists. Not in physics. Concepts cannot, energy cannot exist in physics. Field cannot exist in physics. You want it to exist, you got to turn it into an object. God doesn't exist in physics if God is a concept. If God is love, if God is grace, if God is spirit, poor God, he doesn't exist by definition. God wants to be an object. If God wants to exist, he's got to be an object, and that's not sufficient. He needs to have location as well. Distance from my chest to him. Then he exists by definition, not because I believe or disbelieve or think that he exists or whatever. Okay, next comment from this fellow. Question, comment. Here it is. He says, all good issues, by the way. The definition of science, the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. My, that's a lengthy statement. Does this hold any water? Does this can this pass the test? Well, let's see, let's find out. What this guy did was he defined something that kindergartners do. Okay, and this is what they do. They do activities. They study whatever they study. Everybody studies. Doesn't mean you understand or know or can explain, but everybody studies. They also observe behavior. Okay, they observe all around. They observe behavior of fish, of children, of dogs. You know, they observe behavior. They do experiment with structure. These kids are playing with blocks. Okay, so they're doing a lot of experiments there, right? Learning a lot. And so are these people kindergartners scientists? Because according to your definition, they meet all your criteria. Here we have the biggest scientists in the world, or the smallest. maybe they're pygmies or eunuchs or whatever, little guys. Yeah, science is not about any of that. Science is only about explaining a phenomena objectively. Science had better be objective. Because if we're going to introduce subjectivity, then we go into religion. Then it's your opinion against my opinion, against his opinion. We get in these battles of opinions. But if you put a mechanism on the board, on the screen, and you say, look, this is how this works. This is how a magnet works. And you just look at the mechanism objectively and understand it. Okay, now you learned something. You learned a mechanism. Whether you believe it or not, that's religion. That's your personal religion, your personal biases, whatever. Okay, but what you showed on the screen, the mechanism, that's objective. People see it, understand it, we're done. That's science. That part was science. It was so swift that it went by. Okay, that's the part that was science. The rest is all opinion, mere opinion, as Democritus would say. Okay, another comment. Got two more. This one and another one, or a question. And this fellow says the following. If I can get it up there. Okay, he says the definition of science. Oh no, I just got that. I got the wrong one. I don't know. Repeated the comment. He said something about, what was it? He said something about inventing his own definitions. In other words, he's accusing me of inventing my own definition, saying, "Oh well, everybody's going to invent their own definition. What's this going to be? You know, we should return to to what we had in the old days. In other words, ordinary speech, right, or the definitions of the common dictionary." Okay, and so all I can do is answer him. Yeah, because I think I copied the same thing twice. Okay, sorry about that. Anyways, here it is. Whether it is your or somebody else's definition, it doesn't matter. You must justify and defend it. That's it. You can come up with any definition. It doesn't matter who came up with it. It really doesn't. You want to give him a medal for it? Go ahead. But it doesn't matter who came up with the definition. It matters that he can defend it. And if we have definitions of ordinary speech which are brought into science and they can no longer stand, the definition that they brought in with them, the definition, a given word brought in with it, then it has to be changed. And humans create new words every day, and both in ordinary speech as well as in technology and science. So, language changes over the centuries. I'm sure we don't speak the same thing as Chaucer did, hundreds of years ago, okay? Keywords that make or break a theory are the ones that need to be defined. So we don't define every word for the purposes of physics or science. We just define those that are going to make or break your theory. If you're going to talk about the word object and you're saying, well, this is an object, and you're saying that time is an object, or you're saying that field or force or any of those words or energy is an object, well, then we have a problem, because I don't see it as an object, so we need for you to define the word object. And you guys say, well, it's the word from ordinary speech. Well, ordinary speech says see or touch. I can't see energy. I don't know if I can touch it because I touched something. What is that something? I mean, did I touch energy or did I touch the air? How do I know that I touched energy instead of air or whatever? So no, you can't touch energy because energy is a concept. And so we need to define what an object is for the purposes of physics, and can't use the definition of ordinary speech, which is typically, or the one used anyways, by mathematicians, is see and touch. And we have a problem with that definition, first of all, because you need some other object to do the seeing and the touching. That means you invoke an object to define the word object. So it's a circular definition. But aside from that, see, touch is the wrong criterion, because because see and touch are verbs. And before you can go to verbs, you have to define what an object is. Shape is not a verb. No action there. Shape is a static concept. Language is about communication. So if we're trying to communicate, we better have our language straight, and we can't just say, well, this is how we used it traditionally. Well, we don't care about tradition, because if you're not communicating your ideas crisply, then, what's the purpose of that definition from the dictionary from ordinary speech? And if the language is faulty, there is no communication of ideas, okay? So language has to be very precise, very stringent, okay? You can't define rigorous. You can't define words just in any old sense for the purposes of physics, because physics is different than ordinary speech. There you can say anything you want. You can say, because you're not proving anything. You're not trying to convince someone something. In ordinary speech, it's when you go to physics that people, at least the mathematicians, try to convince people, and that's when they bring these words of ordinary speech. Now, if you're going to convince someone, you're going to persuade someone, at least get your language straight so that we can find out whether what you're saying is valid or not, whether it's worthy of merit. Okay, so if you're going to come into science, you can't bring the words of ordinary speech, because we are going to criticize those words, attack those words, which suddenly have no meaning in science for the purposes of science. And you might say, well, let's invent a new word. No, we don't have to. We just need to be precise with our language. We need to find out exactly what an object is, what exist means, so that anyone who uses the word exist and tries to act like a scientist, well, he better know what the word exist means. And the two words no one has ever defined are object and exist. And that's where the problem is. That's why people talk in circles about whether God exists and whether God is an object or a concept and so on. Okay, last comment from this fellow. Hope I got this one right. uh, if I can get this thing up there. Okay. Okay, here it is. Weights dropping from extreme height previous to Galileo is not, or not, is an experiment with 100% repeatable results. Okay, yeah. GG meaning me, okay, is okay with this experiment as science, just like his demonstration of laser shining on needle for interference pattern. Okay, so let's answer this gentleman. Last answer here for tonight. Then we adjourn to, what is it, Wednesday? Okay, here are the answers to that. Doing experiment and observing is not science. Anybody can do that. Anybody can do an experiment. Anybody can observe. That doesn't mean you can explain what you observed or how the experiment was carried out. And I'm not even talking about invisible phenomena. I'm even talking about visible. I mean, not because you know how to run a car and say, well, I'm going to experiment. I'm going to sit in the driver's seat. I'm going to drive it. Does that mean that this fellow knows how a car works? You know, so the fact that you do something and that you observe it doesn't mean that you understand it, that you understand the causes or mechanisms. The trick is to explain the mechanical cause. That's where you have to use your brain. That's where it hurts. Can't explain this magic trick with particles. For example, push gravity as quantum attempts to do. Can't explain this trick by warping concepts such as relativity that warps time. And that's why in science we define the strategic words that make or break our theory, because you need to use them consistently, rationally, scientifically. And the purpose of running the needle experiment was not to describe it, but to explain it with the electromagnetic ropes. Okay? Because one thing that quantum cannot do is explain the needle experiment. They need to bounce the little balls against the windowsill of the slits. But if you remove the slits and just leave the needle, then now the little balls have nothing to bounce against to come in and interfere with each other. So you cannot explain the needle experiment with quantum. That was the point, not the experiment. You're focusing on the wrong issue there. And the other one is to explain it with the ropes. So we can explain it, and the experiment was not to say, oh, we do experiments in science. No, we don't do experiments, we explain them. It's the explaining part that was science, not the doing the experiment. Okay, with that, I'm going to see you on Wednesday. We'll see you then.